Hi, my name is Samantha Dragosanovis, and I am doing my presentation on Pathway Case Connections 2. So for the first connection that I did was for Case 1. A little overview of Case 1. Question asked, pyruvate kinase catalyzes the rate-limiting ATP generating step of glycolysis in which phosphoenol pyruvate PEP is converted to pyruvate. Multiple isoenzymes of pyruvate kinase exist in mammals, type L, which is found in the liver and kidneys, type R, which is expressed in erythrocytes, type M1, which is found in tissues such as muscle and brain, and type M2, which is presented in self-renewing cells such as embryonic and adult stem cells. So the question was, how does pyruvate get regulated in the cell? So one of the main ways that pyruvate is regulated is allosterically by intracellular signaling pathways and metabolites. Per Israelson's article, this means that PKM2 integrates signaling and metabolic inputs to modulate glucose metabolism according to the needs of the cell. Basically, that means that PKM2 can serve as an inhibitor or activation site or both. So it's the regulation by end product inhibition and regulation by interconversion of active and inactive forms. FBP is also notorious for serving as the binding act to increase PEP binding, promote tetramerization, and stabilize the enzyme tetramer in the active state. Each PKM2, PKL, and PKR subunits contains one binding site that is specific for FBT and distinct from the active site. PKM1 does not bind FBP due to structural differences at the FBP binding pocket. However, PKM1 isoform naturally exists as a stable tetramer that has high constitutive activity rendering it insensitive to most allosteric effectors that act on PKM2, PKR, and PKL. Basically, they have identical kinetic parameters and are both logged onto the same three-dimensional conformation. So other ways that PKM2 is regulated is through amino acids and non-glycolytic metabolites, which allow coordination of PKM. This allows the coordination of PKM2 activity with metabolic fluxes and other pathways. These effects usually require very high concentrations and don't usually have a high visible effect. PKM2 can also be hormonally regulated. Usually it is through insulin and epinephrine that have been suggested to modify the regulatory influence that adipose tissue may have on pyruvate dehydrogenase. This is per Jungus's article on the regulation of pyruvate. So many types of cancer cells are predominantly glycolytic and overexpress the oncoprotein MYC. Interestingly, the classic oncoprotein MYC has been found to promote preferential expression of pyruvate kinase type M2 over pyruvate kinase type M1. Per Harper's textbook, in Chapter 17, glycolysis proceeds at a high rate, forming large amounts of pyruvate, which is reduced to lactate and exported, producing an acidic local environment in the tumor. Glucogenesis in the liver uses lactate for the energy, which is an expensive process. This is responsible for much of the hypermetabolism seen in cancer cachexia. So what other pathways may cancer cells be diverting substrate to? So PKM2 is usually found in cancer patients. Per the Warburg effect, mTOR was termed to be a key activator. Sun et al. Demonstrated that PKM2 was a crucial glycolytic enzyme in the oncogenic mTOR-induced Warburg effect, in which hypoxia-induced factor 1A, HIF1A, and CMYC HNRNP cascades are the transducers of mTOR regulation of PKM. Insulin also upregulates PKM2 through mTOR and phosphatidylcytide 3 kinase, which is mediated in HIF1A induction. However, ROS is the reason for the reduction of PKM2 activity. An overview of the tumor cell metabolism article, which is referenced at the very bottom. Here's an overview of why this might happen. So cancer cells usually use glucose at higher rates compared to non-cancerous cells, but a smaller fraction for oxidative phosphorylation, which enables cancer cells to incorporate a greater fraction of glucose metabolites in macromolecule synthesis instead of expending it on carbon dioxide production. Anabolic metabolism shuns glucose-carbon from glycolysis to biosynthetic pathways like the pentose phosphate pathway PPP. The PPP produces ribose 5-phosphate and phosphoribosyl pyrophosphate PRPP, which is required for nucleotide biosynthesis. PPP also generates NADPH, which in turn supports the proliferation of cells. Hence, PKM2 also helps in the proliferation process and is the main reason why PKM2 is found in cancer cells. PKM2 is also responsible for the final step of glycolysis and is key in this process. Preferential expression and allosteric and enzymatic activity of PKM2 provides the cancer cells with a growth advantage in vivo without the accumulation of ROS. This was basically an overview of why PKM2 is so. Moving on to our second case study as case 4. So a previously healthy 2-month-old female presents with jittery spells several hours after breastfeeding. Her mother reports she has not given the baby anything to eat other than breast milk since birth. The baby has only recently been sleeping for more than 2 hours between feedings, and that's when the mother reports these symptoms started. Laboratory results are consistent with hypoglycemia, low blood glucose, but are otherwise unremarkable. Epinephrine is administered and there is no increase in blood glucose, but there is an increase in blood lactate. So in this, it was asked for us to think of what pathways might be activated by this hormone. They also decided to give us information that a physical exam revealed a liver edge 4 centimeters below the right costal margin, percussion of the right chest and abdomen, which confirms hepatomegaly, which basically is an enlarged liver. Blood glucose levels increased after breastfeeding, but she cannot maintain the blood glucose levels with the normal range during fasting. I decided to look at the 4 diseases that were presented to kind of give me an overview of canceling out what the patient was not experiencing and what she was, and rule out from there. So the first disease given was hereditary fructose intolerance, which for this, the symptoms are nausea, gas, chronic fatigue, and malabsorption. The patient did not have any nausea, gas, chronic fatigue, potentially malabsorption, but there wasn't really any clear indication because malabsorption is more based off of the nutrients, and there wasn't a clear indication of which nutrient she was lacking. More so it was just that she couldn't pull down lactate. Galactosemia, which is loss of appetite and vomiting. The patient didn't have any of these symptoms, so I knew it wouldn't have been this specifically. Glycogen storage deficiency. So a big indicator for this one was the enlarged organ symptoms. So the patient did have an enlarged liver, definitely have hypoglycemia, and did have high levels of lactate, which with glycogen storage deficiency, you can't mobilize glycogen, which with the symptoms that typically present and what the patient had, it was a very similar indication from the symptoms and what she was presenting with, but I decided to also check the last one just in case. So glucose 6-phosphate dehydrogenase deficiency. So the symptoms are anemia, fatigue, dark urine, and jaundice, also pain in the abdomen and the back. So the patient didn't have any of these symptoms as well, or none that were presented to show these. So I went with glycogen storage deficiency as what the patient had. Here are my references attached. Thank you for your time.